When we talk about the derivative, we think about a difference quotient that looks like this, f of x minus f of a over x minus a, and we think about the limit as x approaches a. We say that the function f is differentiable at x equals a if this limit exists. If the limit exists, it's differentiable. If the limit doesn't exist, it's not differentiable. And so this is the study, or this is the concept of differentiability. It's just a word to indicate that this limit exists. So examples of functions that are differentiable are things like polynomials. Polynomials are differentiable no matter which polynomial we use. If we put that in for f of x, this limit will exist, and we've seen examples like that. Another type of function that always turns out to be differentiable is things that look like x to the c, as long as x is greater than 0. So for both polynomials and things like x to the c, we've used the power rule to actually figure out what the derivative is. And this applies to a lot of things. So c can be any number at once. So for example, if f of x is equal to the square root of x, that's actually of this form because it's equal to x to the 1/2. In this case, c is 1/2, and this function is differentiable as long as x is greater than 0. And so these are two types of functions that are always differentiable, and we'll see more as we progress through the course. One important thing to remember about differentiable functions is that if a function is differentiable at x equals a, then it is also continuous at x equals a. So this means that this concept of differentiability, in order for this limit to exist, in order for a derivative to exist, the function has to be continuous. Now the reverse is not true. If it's continuous, it doesn't have to necessarily be differentiable. But in this direction, it's always true. So this is an idea of differentiability. And we'll see more about functions that are differentiable versus functions that are continuous in the next video.